In this video, I'll be going through all the different kinds of NCEA physics equations, roughly from easiest to hardest. Now, I won't be going through every single equation since the process is the same for a lot of them, but I will aim to cover most forms. We're going to start with one-step equations. First up, v equals d over t for d. To solve this equation, we need to move the t onto the side of the v. To do that, we can multiply both sides by t, remembering that we need to treat both sides equally, otherwise they won't equal. That gives us vt equals dt over t. T divided by t is 1, so these appear to cancel, and that leaves us with vt equals d, or flipped around, d equals vt. Next, let's solve v equals f lambda for f. For this, we want to move lambda onto the side of the v, to do which we need to divide both sides by lambda. That gives us v over lambda equals f lambda over lambda. Since lambda divided by lambda is 1, these appear to cancel, which leaves us with v over lambda equals f, or f equals v over lambda. Next up, SISO equals f squared for f. To solve this, we need to get rid of our square. In order to do so, we need to square root both sides. Now the square and the square root essentially undo each other, which leaves us with the square root of SI times SO, or f equals the square root of SISO. Now let's move on to two-step equations. Solving v equals d over t again, but this time for t. Now I'm going to show you the way we solve this, and then I'm going to show you a bit of a shortcut way of thinking. Our aim is of course to get the t by itself. Our first step is a little bit counterintuitive though. I'm going to multiply both sides by t, and in a moment I think you'll see why I've done this. T over t is 1, which means these effectively cancel, which gives us vt equals d. Our next step, in order to get t by itself, is to divide both sides by v. V over v is 1, meaning these effectively cancel, and we're left with t equals d over v. Now let me show you that shortcut way of thinking. When you have an equation of this form, something equals something over something, it turns out that you can swap these two around, so that v equals d over t, but swapping the v and t equals d over v. All we did is swap these two around. Once again, this works for every single equation of this form. Now let's solve E equals half mv squared for v. Since we want to isolate our v, we want to do two things. We want to eliminate the half m, and we also want to eliminate the square. BEDMAS dictates that we have to first remove the half m. So we need to divide by half m. Half m over half m is 1, meaning that these terms effectively cancel, leaving us with e over half m equals v squared. Our next step is to square root both sides to get rid of the square. The square and the square root effectively cancel, and that leaves us with v equals the square root of e over half m. This can also be written as 2e over m. Now just quickly, another way of doing this is to get rid of the half first by timesing both sides by 2. That would give you 2e equals mv squared. You then divide both sides by m to get 2e over m equals v squared. And finally, square rooting both sides gives you the square root of 2e over m. Next up, vf equals vi plus at for t. We first subtract vi from both sides. Now since vi minus vi equals 0, these effectively cancel, which leaves us with vf minus vi equals at. Our last step is to divide both sides by a. A divided by a equals 1, so these effectively cancel, and that gives us vf minus vi divided by a. Next up, d equals vi plus vf divided by 2 times t for vi. So let's first multiply our 2. That leaves us with 2d equals vi plus vf multiplied by t. And so it's worth pointing out that this equation can look a bit confusing if you're not used to how fractions are used in algebra. When we write vi plus vf over 2 times t, This can also be written as vi plus vf over 2 in brackets times t. We can also think of the t being in the numerator. We could even think of this as t over 2 times vi plus vf. If any of these surprise you or you're sitting there shaking your head, you'll definitely want to spend a bit more time looking into this algebra. My next step is to divide both sides by t. That gives us 2d over t equals vi plus vf. And my final step is to subtract vf from both sides. That leaves us with 2d over t minus vf. For the last of our two-step equations, d equals vit plus half at squared for t. Now, if you ever need to solve this particular equation for t, vi will always be 0. The reason this is the case is because if vi wasn't 0, then you'd be left with a quadratic, an equation that you're never expected to solve in NCEA Physics. So our first step here is to recognize that vi is 0, and trust me, it always will be if you're solving for t. And what that means is that this term disappears, because 0 times t is 0. Every year I'll see a student who will not disappear that term and try to solve this equation for t. It absolutely can be done. It is just very difficult to do for many level 2 and some level 3 students. So the equation now becomes d equals half at squared. Our first step is to divide out the half a, and that gives us d over half a, but as I explained earlier, divide by half is a times by 2, so we can instead write 2d over a. To get rid of our square on the t, we square root both sides, and that leaves us with the square root of 2d over a. Let's now move on to some Pythagoras. We'll start simple by solving a squared equals b squared plus c squared for a. This is just a single step. We need to square root both sides to get rid of the square above the a, and that gives us the square root of b squared plus c squared. Let's now solve this for b. Our first step to isolate the b is to subtract the c squared from both sides. And now, just like last time, we need to square root both sides to get rid of the square above the b, which gives us the square root of a squared minus c squared. Staying in the theme of trigonometry, we'll now look at SohCahToa. Taking our Ka relationship, we're going to solve cosine theta equals a over h for a. This gives us a simple one-step equation where we just need to multiply both sides by h to move it to the other side. And that gives us a equals h cosine theta. We'll now solve the same equation, but this time for h. Now, if you recall earlier on in the video, we did the problem solve v equals d over t for t, and when we did that, I showed you the long way of doing it, where we multiplied by t, and then we divided both sides by v, and that solved our equation. But I also explained that if you have an equation of this form, you could also just swap these around. It's another way of thinking about this problem. Well, the time has come, and we indeed have an equation that is of that same form. We can now confidently use our shortcut, and we can swap our cosine theta and our h around, which gives us h equals a over cosine theta. Let's now look at Snell's law, which we'll solve firstly for n1. Our first and only step is to divide both sides by sine theta 1 in order to move it to the other side, which gives us n2 sine theta 2 divided by sine theta 1. Let's now solve this for theta 1. To do so, we're going to do two steps. Firstly, we need to get rid of the n1 from this side, so we're going to divide that out. And then we need to get rid of the sine, for which we need to use inverse sine. Now, I'm going to take an aside here to hopefully clear up some misconceptions that you may or may not have. If we have the term sine x, it's important to clarify that this is not sine multiplied by x. This is not the case. And because this is not the case, you certainly can never divide by sine by itself. If this seems confusing, consider the square root of 2. Now, if I was to get rid of this square root, I hope that you see how absurd it would be for me to say that I was going to divide by a square root. Hopefully you understand that if you ever have a square root, it has to be the square root of something. You cannot have a square root by itself. And also that this is certainly not the square root times 2. These two examples are the same. Square root is a function, as is sine. A function refers to a special process that is being applied to whatever its contents are. And as such, you can never have a function without some contents. And so if we have sine of x, how we get rid of the sine is to use a special function that is designed to do exactly that. And that function is aptly called sine minus 1. And we can apply that to sine of x, and what happens is it essentially unravels the sine. You could also get away with saying that they cancel out, although I'd certainly want to dissuade you from thinking of sine minus 1 as being 1 over sine. It definitely is not. So the result of sine minus 1 of sine x is just going to be x. And so in this case, I'm talking about the sine function, but the same applies for the cosine and tan function, which have their own inverse functions. So if we take the sine minus 1 of both sides, our sine minus 1 undoes our sine, and we're left with the inverse sine of n2 sine theta 2 divided by n1. Let's now look at parallel resistance. So this here is the equation for 3 resistors in parallel, finding the total resistance of them. Let's try solving this for R1. Now my first step is to subtract 1 over R2 plus 1 over R3. That will get our 1 over R1 on its side by itself. That gives us 1 over RT minus 1 over R2 minus 1 over R3 equals 1 over R1. Now you might note that we seem to have a plus here that turned into a minus. The reason it did so is because we're subtracting. And now our next step, flashing back once again to our solving v equals d over t for t, remembering that we can swap these two terms for this equation and any equation of its form, we once again find ourselves in that situation. And that gives us 1 over RT minus 1 over R2 minus 1 over R3. Let's now move on to a few level 3 equations, starting with Newton's gravitation, which we will solve for R. Our first step is to once again use our little trick, where we can swap our F for our R squared. Our next step to get rid of the square above the R is to square root both sides. And that gives us the square root of GMM divided by F. Let's now look at the Doppler effect. We're going to solve this equation for a receding source for our Vs. Now, although the equation is written most often with our F out the front, just for clarity and to avoid confusion, I'm going to write the F up here to show that it is indeed in the numerator. What I'm first going to do then is swap our F prime for our VW plus Vs, a process that you should be well familiar with now. Our final step is just to subtract our VW from both sides. And that's done. Next, let's solve this equation for VW. This is going to require a few extra steps. What I'm first going to do is multiply both sides by our denominator VW plus Vs. Now I'm going to expand the brackets out. We now want to group all the VW terms on one side, so I'm going to subtract this term here from both sides in order to get it on the other. Now to consolidate our VWs into one, I'm going to factorize the VW out. Our last step is just to divide both sides by our bracketed F minus F prime. And that gives us F prime Vs divided by F minus F prime. Let's now look at our center of mass equation, which we will solve for x1. Our first step is to get rid of this denominator by multiplying m1 plus m2 to both sides. Next, we can get rid of our m2x2 term by subtracting that from both sides. Lastly, we divide both sides by our m1. And that gives us xcom times m1 plus m2 minus m2x2 divided by m1. Let's now solve this for m1. To do that, we'll start off the same as last time by multiplying both sides by m1 plus m2. Next, I'm going to expand our brackets out on our left side. Now I want to group our m1 terms together. So I'm first going to subtract our m1x1 from both sides. And now to get rid of our m2 term on the left, I'm going to subtract xcom m2 from both sides. Now I'm going to factorize our m1 out on our left. And we might as well factorize out our m2 on the right, just to make things a bit more tidy. Our final step is just to divide out our brackets here, which gives us m2 times x2 minus xcom divided by xcom minus x1. Let's now do the simple pendulum, which we will solve for g. Our first step is to get rid of the 2 pi by dividing it from both sides. Now to get rid of the square root, we need to square both sides. Now to recall our trick, we can swap these two terms here, which gives us L over T over 2 pi squared. Now by expanding our square out, we could also write it this way. Or, since a denominator in a denominator becomes a numerator, we could write it like this. Now for our last example, we're going to look at simple harmonic motion and specifically acceleration. Specifically this equation here, which we're going to solve for t. Our first step is to divide out our front term here, negative a omega squared. We now need to unwrap our sign, for which we're going to use our inverse sign. For our last step, we're going to divide out our omega. And we're done.